Okay, hello everyone. Today we're talking about doctrinal adjunction.
What's a doctrinal adjunction?
Well, you tell me. So, you, what do you know about doctrinal adjunction, or what does it make you think of?
Um,
What's a doctrine?
yeah, good question. My guess is a doctrinal. It makes me think of some sort of like two categorical version of adjunctions, and you're working in some doctrine.
A two-categorical version of adjunctions, and you're working. I'm just repeating what you're.
In a good tone.
Yeah.
Yeah,
Okay.
that's what it makes me think of.
Okay. And you're working in a doctrine, did you say?
Yeah, I'm not too sure what that means.
Okay.
I'm hoping you're going to tell me.
Well, so I believe here we can treat the word doctrine as like a two monad. So I think the idea is, and I'm not sure, but the idea is like a doctrine is a higher notion of theory,
Okay.
right? So a theory, like we can think of a Levier theory, which is equivalent to a finitary monad
Hmm.
on set. If we want to describe theories, we can describe monads on set. Now, if we want to describe, and that algebras for that give a notion of a set with some extra structure on it.
Just a model for the theory.
Yeah. Now, if we want to go look at higher theories, we might look at models for theories on categories,
Hmm.
right? So instead of looking at monads on cat, we're looking at two monads on two cat.
Cool.
And so when people talk about like KZ doctrine,
I've heard that one.
yeah. So that is a two monad. That's the same
Okay.
thing as a lax idempotent two monad.
Okay.
So this the doctrine here, I think we can just treat as two monad. The point is to any two monad, we get a notion of like algebra for a two monad in the same way we do
So is it a two monad on a two cat or on two cat?
on any two category.
Oh, okay.
Two
Okay.
cat, in particular, cat,
Okay. Yes. Cool.
right? That's
Cool.
sort of the favorite. In the same way that set is like
Is
the
is the yeah.
prototypical thing which bears a monad. Um, Okay, so so right, it's adjunctions to do with, and it's somehow related to two monads.
Okay.
And I'll say it's related to algebras for two monads, in
Okay.
fact. And okay, so here's some motivation, and this is when I first heard the term doctrinal adjunction.
Hmm.
So a fact you may know, if you've got a monodal category, M, uh, one tensor.
Hmm.
Um, there's a natural notion of morphism of monodal category. In fact,
Hmm.
there's a few.
Yeah.
Um, right. So, in particular, we could look at like a lax monodal functor.
Sorry, I'm just gonna.
Oh, you want that to be an M prime?
Well, I just think yeah. Let's be a bit more.
Okay, sure. Okay, so what is a good notion of morphism here?
Hmm.
Well, we might ask that it strictly preserve the tensor product,
Yeah.
but maybe you know a more natural thing to do in this setting where we've got like weaker notions is to define it as one of these weaker
Yes.
notions. So we might say it's a functor from M to M prime
Hmm.
such that we've got this rule that if we've got X and Y in M,
Hmm.
we can map across and then take the tensor, or we could take the tensor and then map across. And one thing we could do is ask that these be equal, or that we've got an isomorphism between them,
Hmm.
or a morphism
Yeah.
in one or the other direction. So let's say we want a morphism in this
Is
direction.
there? I was gonna say what like. How do you know? This is one I've never got. Like, because one would be lax and the other's oplat.
Mhm.
How do you which?
How do we decide? Do
How
we
do you
just
decide?
randomly pick for
Yeah.
each instance?
Because I would have guessed, right, that the natural one
Mhm.
would be the one that your thing goes from tensor to tensor prime. So I would have guessed the natural one would have been this direction because this term involves tensor, this term involves
I
tensor
see.
prime, you know?
So they're both equally as natural.
Okay.
But I guess the question is which one's lax and not
Yeah.
lax? How do we decide? So there is a reason to call this one lax, and
When you
we'll
say this one, the one in black.
the one in black.
Ah,
Let's get rid of
okay.
this one. And
Thank you.
so and we'll see what that reason is.
Okay.
And
Okay.
it's not that like it's that we've made it that this is consistent with a bunch of other things.
Okay.
If we wanted to swap this, then we should swap a bunch of other
Okay.
notions of lax.
Okay.
Okay, so this is a lax morphism, and the thing we
Mhm.
drew was an uplax morphism. And obviously, there's then some coherence conditions
Mhm.
relating F2 with the associators and so on. There's another map, right? Another part of the data of a lax monodal functor. So this tells you how like binary products are sort of laxly preserved, and there should be something that tells us how nullary products are laxly preserved. So the two things you might want to compare are f of one and one at f.
Yeah.
Sorry, and just one in here. Okay, and which direction do
The
you
bad direction, surely. Wait, yes, because this is one prime, right?
Yeah.
So to me, this is the direction that's not natural. So, but same as the last one, it goes from the prime to the not prime.
Yeah, exactly, right. So you think of this as we map across and then we take the tensor.
Yeah.
Whereas this is we take the tensor, the map across.
Yeah.
And this is here, we're taking the nullary tensor, then mapping across. And here we're taking the nullary map across and then tensor.
That's right. Okay.
Yeah. Okay. So I tried to trick you there, but so let's just do this.
Okay.
And yeah, you're right, the prime goes there. So so this is a lax.
Sorry. There we go.
And we're going to call this F0. Okay. This is a lax monodal functor. Okay.
Which means a monodal functor belonging to Steve Lack.
No. Lax. Okay. Now, what happens if we have so in certain contexts, adjoints naturally inherit like structure preserving properties. So like, I believe if you've got an abelian functor, a map of abelian categories,
Sure.
and then an adjoint on the underlying category, then that naturally becomes an abelian functor.
Okay.
I believe that's true. I might be completely wrong. But
like, is this just to do with the fact that like adjoints preserve limits or co-limits, and if your property is limity or co-limity?
Well, that's sort of something we'll talk about later.
Oh, okay.
But so do you know what happens if we consider, so we've got this monodal functor f, which is, we can consider the ordinary underlying functor f from n to n prime.
Yeah.
Let's say we've got a left adjoint to f.
Okay.
What can we say about that left adjoint? Do you know?
That's a great question. So you're saying, so you have some like, so you now have some L, which is a left adjoint to F. What can you say about L?
So it's a left.
Isn't it? I just know this from like parroting from being in a room full of higher category theorists. Isn't it like true that like L is strict or something? Like L is automatically strict, right?
No, but that's sort of close.
Okay, pseudo? Lax.
So let's find out. So here's another way of describing. So we've given like the biased. Well,
yes.
Okay, but and I'm going to like, we're going to ignore this data for now, and we'll sort of wave our hands and say why we can just sort of do the proofs for this property. So let's say, I want to call this G actually. I can't.
And the bottom guy F?
And the left adjoint will be F.
Sorry, I accidentally erased something.
It's okay. Okay. So let's assume we have a left adjoint G.
No, a right adjoint G. F is left adjoint to G.
Yeah. But we're assuming we have a left adjoint to G.
Sorry, to G. I think you said we have left adjoint G.
No, that's what I said.
Sorry.
Okay. So here's another way to express. Now we're going to use string diagrams, and I hope I'll convince you that,
that they're good now.
That they're good.
Okay.
So what's another way of writing this? Well, so this is.
Okay, yeah.
I mean, you can come up with your own string diagram.
Well, here's the string diagram I would draw, having just seen a great talk in the cloakroom yesterday, in the Oxford seminar yesterday. I would write this guy over here as something like, you know what? I'm going to write my string diagrams right to left. I feel more people should do that, right? You could write this as like this. And then this one on the left, I would write as this.
Oh.
As in like here, I've done G, and then I do a, I guess I should have two wires going into one. I don't really understand I don't really understand string diagrams. This is evident. But as in like this basically looks like the thing about deterministic maps, right? It's like you can either like do G before the copy or do G after the copy.
Yeah.
And like they're different copies, right? Like this is tensor prime and this is tensor.
Yes. So these are good depictions of the things we've got on the left and on the right.
Okay.
So um,
Oh, I actually did them left to right by mistake in the end. Okay.
yeah,
That's fine. That's good.
that's
I'm
okay.
happy with that. Okay.
So like this dot here is your tensor prime.
Yeah.
Right, okay. But we want to talk about this map G2 between them.
Oh, yeah. Okay.
So we run out of dimensions. So what we're going to do is we're going to squash this.
Okay.
And we're also going to do it right to left, as you suggested.
Good.
So imagine this. I can't do something clever like rotate here, can I? Oh, yeah.
Whoa.
Wow, okay.
Okay. Beautiful.
Imagine
Yeah.
none of these were labeled. Okay, so on the left, we've got this is G squared. It's
Okay.
taking a pair of things and doing a
Sure.
redo it. And then we've got tensor prime.
Yeah.
Sorry. Yeah, tensor prime.
Prime.
Okay.
Wait, and then I want to do the other one.
Okay.
So this one, when you rotate it, can you rotate it for me,
Sure.
please? I don't have the rotate button on my thing.
You
Okay.
do.
So this one here is when you do on the right, you've got a thing called tensor, and on the left, you've just got a thing called G.
Yeah.
Oh,
Okay.
okay. Okay.
So we've got a string diagram who's like we've got a morphism.
Yeah.
And I'm going to write neither right to left nor left to right. I'm going to write bottom to top.
Top. Yes. Okay. I've seen you do this before, and I've always wondered what you were
Yeah, so
doing.
there is a reason, but so one reason to write like right to left is that you don't have this disparity between diagrammatic and
Sure.
ordinary composition ordering. And that's also why you go bottom to top, because if you want to read like vertical composition, so the fact that we call it like horizontal and vertical composition of two cells is sort of consistent with this.
So you're going to draw something that starts like this and ends like this, right?
Yes.
Okay. I haven't given you much space to do it in, so you better be good.
Well, it's just a primitive.
Okay, yes, sorry, okay.
Okay. Cool. Now, so the claim is if we have a left adjoint to G, it naturally inherits an oplax structure. Now, oplax goes in the other direction.
Yeah.
So what we want to do, and maybe you can have a go at figuring it out, is we want to give an oplax morphism. So we're going to call the left adjoint F. So we need to give something F squared after tensor. Right, F is going from here to here.
So you'll do.
Sorry, not F squared. Sorry, I'm
No,
tipping it the wrong way around.
Yeah.
We want F after tensor.
Yeah, you like double compensated.
Yeah. F after tensor.
Going up to tensor prime and F squared.
Right, and sorry, this should be tensor prime. F after tensor prime. And then somehow
do something. Okay. Well, I guess what would be helpful is if I knew what having an adjoint gave me.
Okay. So what equations do we have?
Oh,
what two cells
do we have? Goes to FGF goes to 1. Like you have some.
So we've got FG, metro transformation from FG to the identity on C. M, whoops. And we've got the identity on M prime into GF. Okay. So this we're going to call epsilon and eta. And so what does this look like? Well, this starts from F after G. And it goes to the identity. We're going to represent the identity as like nothing.
Nothing, sure.
Right.
Also, is this cups and caps? When people talk about cups and caps.
Yes, I guess this is at least one of those instances. Okay, so we've got these two maps.
Okay.
These are two cells, and we know we've got these triangle identities.
Yes.
Which say precisely that if we do an epsilon and then an eta, well, in this sense, and obviously this is like, sorry, I got this wrong around. Eta and epsilon, and this is saying that this is actually G.
Yeah, you can yank. This is the yanking, right? I've heard of this.
Yeah, but just reading this out, I've got G epsilon after eta G, and right. The reason we go bottom to top is so I can read it top to bottom.
Yes.
Is equal to
see.
the
Okay.
identity on G.
Yeah.
So we've got this one becomes a string, and we've got
The
this
other
one
one
becomes a string, and
Yeah.
this is F, and this is G.
Cool.
Okay,
Okay.
we can get rid of all of this now.
Yeah, because I've in my brain internalized it. Cool.
Okay. So
Ah, man.
we are allowed to use either of these caps or cups, and we're also allowed to use G2.
I see. Okay. Okay. Interesting. Okay. And are we allowed to, do we have like a swap or anything? Are we allowed to use that?
No,
Whoa.
this is not like you can't just
Well, yeah, because
pass
I'm
straight through.
immediately like the only thing we ever have that has a tensor on it
Mhm.
always has a G on the left. And this guy, the leftmost thing is a tensor. So like, how am I gonna? So I realize when I point at stuff, it doesn't actually
Yeah.
appear on the screen. But
So we've got
okay.
at most one way of producing a tensor,
Yes.
right? There is only one two cell we can get a tensor
Yeah.
out of,
So
so we might as
there
well.
has to be a G2 here.
Yeah. Well, that's a reasonable guess.
Yes, thank you. Which is going to give me a G out here, and it takes in a tensor prime. You might want to move this guy down, I'm guessing, maybe.
Mm.
And this is a G squared. Or do you not think I'm going to need that much room?
Well,
Okay.
it depends on how big
Okay.
you are.
G.
Mm.
This is a. This is a. Wait, let me get this. This is an epsilon.
Mm-hmm.
Bam. This guy's there. Here we go. G squared.
Mm-hmm.
I don't know what to do with the oh, G squared is just GG.
It's G times G.
G tensor
times. Times in cat, right?
Yeah, but as in, what can I do with like if I have a string diagram which has a G, what can I do to a G squared?
So
I don't know that.
You can take any product of, so like a morphism from G squared to like H squared is one way you could get such a thing, is a pair of morphisms from
G to
H, and then you just take the product. So if you've got like an alpha times beta.
How do I draw a product as a string diagram though? I don't know how to do
Well,
that.
you don't. That's not something that geometric.
Okay. Fine. Okay, so I've got a G squared and I've got an F squared. Wait, am I allowed to just like write like eta squared?
You are indeed.
Whoa, okay, so I didn't realize you were allowed to just
yeah.
Sorry, change my words. Yes, sorry, I didn't realize you were allowed to just do that. Okay, that's cool. Eta squared. Okay. It's so beautiful. I made it.
Okay.
Okay, wait, so what's this told me? Oh, it's told me, okay, so sorry, what did this tell me? It told me that whenever I had a lax right adjoint, or whenever I had a lax functor, if it were a right adjoint, the left adjoint is automatically op lax.
Yes. But, well, I mean, so there are some things to check, like remember F2 had to satisfy some properties.
Yeah, sure.
But
okay.
yes.
Sorry, but the key point there, I was like, but how could it be so when I have a lax monodal functor whose underlying just like plane functor has a left adjoint, it actually is a monoidal adjoint. Like it has oplax, yeah. But like it gets some adjective that makes it be a monoidal functor for free, an oplax one.
Yeah.
Okay, nice. Is it true that if G were pseudo, then F would be pseudo?
No.
Okay. Is it true that if G is strict, F is strict?
That's also not true. So, but there are some other things we can ask. So what happens if we had not just any old adjunction, but a monoidal adjunction? So in other words, F were itself, sorry, like a lax monoidal adjunction.
What does that mean? In terms of unit and co-unit, does that mean something or like?
It does.
Okay.
So what is a lax monoidal adjunction? Well, it's an adjunction in the category of lax monoidal functors and monoidal transformations.
Okay.
So what's a monoidal transformation? Let's say we've got two monoidal categories. We've got, actually, I always want to draw going right to left so that it's consistent with my string diagrams. F and G.
Oh, yeah, okay. I was like, if they're going to be adjoint, they have to point opposite ways, but these aren't adjoint anymore.
No, we're just defining an
Yeah.
arbitrary two cell. So what's special about a two cell between x monoidal functors for it to be a monoidal
Yeah.
functor? Well, so we know that f comes with this.
Oh, okay. I was going to guess. Like, does it just, it also induces something on F2 or something? Like it,
Yeah,
or do you,
so yes, so there's if we've got like uh, f of x, f of x and f of y,
Mhm.
we could do alpha x, alpha y, and then that gives us g of x, g of y,
Okay.
and then we could do g2
Yeah.
and get g of xy.
Ah, okay, wait. So does it say you can slide it past?
Yeah, so push these two alphas through, and then we get alpha xy
Mhm.
after f2.
X and Y.
Yeah.
Okay.
Okay, but there's another way to draw this picture. So uh, here this thing is like G2. So G2 goes from G squared tensor up to G squared to
G
G
and tensor prime.
tensor prime. Okay, and so here what's happening? Well, we're taking f squared.
Uh-huh.
We're doing alpha squared to it,
Yeah.
getting G squared, and then we're doing G2.
Uh-huh.
And over here, what's happening? Well, we're taking
Oh,
f
okay.
squared,
And yeah.
tensor after f squared, sorry.
Mhm.
Then we're doing f2.
And it's just going to be on like the top right leg.
Yeah, and
There's
then
going
we're
to be an
just going
alpha on the top.
ordinary.
Oh, top left, sorry. Why top? Oh, okay.
I mean, well,
Wait, let me think. Okay, yeah.
if it went on the top right leg, it's not gonna.
Oh, it doesn't make sense to go on the top right leg. Yeah, yeah, yeah. Alphas
Right,
turn
right.
Fs into Gs. Okay, yeah,
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 yeah.
sure. Okay,
So the way to think about this, like this picture, we talked about x's and y's. Where
yeah.
do they live? Well, imagine we've got like this map from the terminal category into, what was it, a times a,
Mm-hmm.
a squared. And so what's a functor from 1 into a squared? Well, it's a choice of element
Sure.
in a squared, which is an x and a y. And so we can actually look at each like layer. Might choose a different color. At each layer, we can look at the object. So here we start with, we do f squared on xy, which gives us a pair fx, fy.
Yeah.
And then we take their tensor, that gives us f of x, tensor f of y. And then we get alpha squared at xy, which gives us the alpha x tensor alpha y,
Uh-huh.
right? Which is the morphism up here. Right. So if we were checking that like this thing made
Okay.
sense, we should see that this diagram corresponds to the one above.
Uh-huh.
So at the bottom, we've got fx, I mean, we've got the same thing.
Yeah.
Then we do f2
Yeah.
at xy, and
Yeah.
that's what's happening here.
Mhm.
And then up here, we've got xy, we tensor them with prime, x tensor prime.
F of X, tensor prime, F of Y, right? No?
Well, I mean, so tensor prime here was apparently our A, tensor prime lived in A and tensor lives
Oh.
in B.
Oh, okay. Okay.
Just because we
Okay.
didn't really name
Yeah.
them, but
Okay.
that's what type checks here.
Okay.
So we take the tensor prime with x and y, and then we're in here, and then we take f of that thing, and then we've got this map alpha, which goes from f of that thing to
Mhm.
g of that thing. So it's alpha at x tensor prime y,
Okay.
right, which is this thing here.
Okay. So you're doing some very string diagram magic that I've heard of before, but never done. Like there's some like you read these right to left as some other thing. Like there's some, I don't know if this is worth explaining. I'm happy to like believe it for now. And like I kind
Oh,
of get what you're doing. But this thing
yeah.
of like reading it right to left, where on the right you have nothing, so it's just the identity, and like
Yeah.
you like go right. Yeah.
The point, I guess, is that like these string diagrams, the regions, the spaces are categories.
Uh-huh.
Or like objects in a two category more generally.
Mhm.
These wires are functors.
Yeah.
And these circles, these cells
Yeah.
are two cells.
So it's Poincare dual to what I would
Pasting
expect.
back.
Yeah.
Yeah,
Okay.
exactly. Now you can use them to reason about morphisms in a category because objects are the same as a functor from the terminal thing.
I see.
Right.
Okay.
So this diagram
Yeah.
is like a morphism in the category B. So we get that as soon as the thing on the right-hand side is just a terminal category, which we've got once we insert these lines here, then this is now a string diagram for just a morphism in our category. But the point is that this doesn't actually depend on x and y. We'd say something like, and this is natural in x and y.
Okay.
And that's expressed by the fact that these don't interact, right? If I have some like pair of morphisms, f and g, on x and y, which is the same thing as a natural transformation between one choice and another choice, then I can just slide this up and down,
and it doesn't see anything else.
And naturality says it's
okay.
So yeah, in any, maybe like you need to stare at this a bit longer to sort of see how this picture is the same as this one here, but like you can see that we're doing f2 first.
Yeah.
And then we're doing alpha at the tensor.
Yes.
Whereas over here, we're doing the tensor of alphas at x and y, and then we're doing G2.
I see it. Okay. Yeah, it's doing something clever where it's like these string diagrams are just being read bottom to top. So there's like a whole dimension's worth of information that you could use, and that's what you're using to encode your sort of like you're doing alpha at the tensor, so you write tensor prime and then alpha. Like you're using the extra left to right dimension to say things.
Yeah.
Okay.
Yes.
It's kind of magic. I'm happy to, yeah.
The thing it makes, like, it exploits naturality, right? Like, you don't need to pick an ordering, like, you know, for.
Yeah, okay. Okay. I'm so much to learn about string diagrams. One day I might agree to.
So for now, what we notice is that alpha being a natural transformation, a monoidal transformation, merely means that we can slide it through.
Or you slide through an alpha squared to become an alpha.
We slide through an alpha squared.
Right, just as in like this guy down here is actually an alpha squared, right?
Oh yeah, exactly.
Like,
sure, sorry, yeah.
Okay, that's okay.
So,
but it kind of like, it has to be just because of the type of the thing on the bottom. So,
yeah. Okay, yeah. And we'll see, again, this is meant to be sort of a particular example, like a very illustrative example, but a particular example of something more general.
Okay.
So here we've got alpha squared, which is a bit like we're applying a functor squared to alpha, like, you know, think T alpha. And then we've got this map. So like T alpha, then our algebra map, H, and then we've got some lax morphism.
Okay.
Anyway, so we'll see more string diagrams that look like this and might explain like that this is just one instance of a more general thing. Okay, so that's what a monoidal natural transformation is in general. Now we want to ask what it means for an adjunction, therefore, to be monoidal.
Yes. Okay.
So we want these two maps, epsilon from fg to 1. My pen to be bigger. Epsilon from fg to 1. Oh,
that's too big. I think 3.
I know, we decided 3 is good.
3.2.
No. Epsilon from fg to, maybe can we say that our monoidal categories are C and D rather than M and M prime?
Yeah, definitely. I don't know why you picked M and M prime.
So let's go C tensor 1.
And can the other one be like a box time rather than a... Thanks.
So D box times C. No.
How about this? The word 1.
No.
Okay, fine. I'll accept I.
I mean, it would be better maybe to just use like subscript C and D.
Yes, I'm going to actually do that. No, because then I like I. It's like a boxy version of 1. In the same, I is like the round version of, sorry, 1.
What about lowercase c, lowercase d?
What are you going to call an object?
X.
Okay.
Then Y.
Okay, fair.
Okay, so we've got FG, is that right? Well, I haven't said what these are, right? This is F, this is G. Okay, that's good. To 1C. And we've got eta from GF to, whoops, sorry, from 1D. into GF.
Mm-hmm.
Okay, what does it mean for these to be monoidal?
Mm-hmm.
So let's start with epsilon because this is
Yes.
the one that's gonna be important. Okay, so it says that if I just like blindly copy what we had above, it says that if we've got like 1C2, which goes from tensor, does this sort of make sense? The point is this is a functor.
Yeah, yeah.
It's
Okay.
going to be monoidal.
Yes, okay, yeah.
We'll think about what this
Yeah.
map is, the compositor map.
Yeah.
It's not very interesting. We'll see. And then we've got epsilon squared here.
Mm-hmm.
Right, and this is FG squared.
Mm-hmm.
And this is 1 squared. And then we're going to get a 1 and then a tensor.
One of those should be a box.
No.
Oh,
These functors
one's
both,
C, sorry. Yeah, okay, yeah. Okay.
And
so
this
you
should be
be able
equal to
light it up. I can draw that guy.
Okay.
It's this guy. Such a weird epsilon. First time using one of these.
So it's not 1C anymore, is it?
Whoa there, buddy. I was testing you. Let me do some type checking and think. So this guy is still an FG squared.
Mm-hmm.
This guy is still times. Why is it not? Wait, FG. Wait, which order is this? Is do G, then do F.
FG is do G and then do F.
Okay, like this is normal. Okay.
Yeah. I mean, you can just treat it as FG, treat it as a single symbol. It's the domain of epsilon.
Oh, wait, so is this now 1C squared?
1C squared. No. So
wait, what? Wait, can you scroll up a bit so I can see? Like, what happened with the alpha case? Like, things didn't change there, did they? Oh, it changed from G2 to F2. Things did change.
to, right?
Yeah,
After we push the F through,
of course. Yeah,
it goes to the 2 thing at the domain of the transformation.
So is it just this?
Sorry. Just no.
No. Okay, wait.
So what's the domain of epsilon?
The domain is, oh, sorry. So yeah, is FG.
So it has to be FG2.
Oh, because this wire is now just like an identity wire or something.
Well, this wire is FG.
This wire is...
Right, so
okay,
FG is not the label like at the end. It is the identity of that wire.
Okay, this is, you're teaching me secretly about doctrinal adjunctions, but also string diagrams
Yeah,
at the same time.
This
is like, okay, yeah, okay, fine.
Right, so FG2 is of this form, right? It takes, this says it goes from tensor of FG,
okay,
FG
yeah, okay,
into FG.
Yes, yeah.
Okay.
Yeah. No, okay, I do see that. That's really obvious.
Okay.
I feel like such a bad
Yeah.
student. No.
Okay, so the question is, what does 1C2 look like? What does FG2 look like? They should be expressible in terms of F and G.
Yeah.
Right, like, and well, guess what 1C2 looks like?
So it has to go from 1. So wait, what is the 2? The 2 is the laxy kind of part. It goes from F. So yeah, so normally like, say we have a functor H. What is H2? So if H goes from C to D, H2 is the thing that goes from like it's the H2 at some guy
at a pair XY
goes from the second one, which means I'll have to have done HX first, to okay, so if H is equal to 1, then this just goes X. This doesn't type check. Oh, it does because it's from C to C, sorry. Oh, is it going to be, please be it the identity?
Yeah, it's the identity.
Because it has to go from X tensor Y to X tensor Y.
Oh, sorry. Yeah.
Oh, yeah, sorry. I dropped up different things. Yes, okay.
Yeah. Okay, and that does indeed work, right? So first of all, let's write this FG squared. We can just write that as F squared after G squared.
Yes.
Okay. We don't usually write identities in a string diagram. So
Okay.
this is really just this.
Whoa, that's a way simpler string diagram. Okay.
Now, what about this one? So here we want to
Ooh.
write this as f squared after g squared.
Yeah.
Let's see if you can just... So imagine we're defining a composition of lax... Sorry. We're defining a composition of, yeah, lax monodal functors, and we want to state that the composition of a lax monodal functor is another lax monodal functor. Obviously, the underlying functor is a composition of the underlying functors, but what is the compositor, or the laxator?
The laxator.
I.e., what should fg2 be? It needs to go from f squared tensor after f squared after g squared into f after g after tensor. So let's just see if we can build it up.
Some other string diagrams of this form.
Yeah.
Well, surely shump.
No.
Okay. I wanted it to look like the diagram on the left somehow.
It's I mean, so the point is it won't. Like, it's a non-trivial condition.
Okay. So okay. So and okay, I want to get my so F lives on the box. Wait, so I'm trying to think like what can I do to what? Like F squared and tensor have some guy, right? This is precisely this is F2.
Yeah.
Sorry, the laxator here. So this guy eats one of each. And then what does he spit out? He spits out an F and a box.
Yeah.
Which just like labels the wire. Yes. Okay. But now the point is G2 has a laxator, which spits out exactly what we want it to do. It spits out, oh, wait, sorry, we don't actually need the box, the square brackets around it. So, yeah. Okay, so this is G2. That gives something of the right form.
Yeah. Okay. So I hid the epsilon, right? And there was an epsilon up here, which goes from...
Oh, yeah, which gets rid of it at the end.
Right. And we're going to suppress the identity above that.
This is cool because it says like you take the string diagram on the left and you like pick up that epsilon squared and drag it over the wire. But when you drag it through the wire, it like you need to do something. You get these intersection points, and that's what this F2 and G2 are.
Exactly. And that's a good way to think about it.
And how, like, I'd like to say, because I don't know anything about string diagrams, but I'd like to say that the order here shouldn't matter, right? Like the fact that G2 is higher up the page than F2, or does that matter?
Oh, it does matter here. So the point is we can't deform G2 to be below F2.
So we're not allowed to do this. Like we can't make a wire do this or something.
I mean, no.
Okay, that's fine. That's fair.
Yeah, I mean, like... No, because I mean, the idea is you meant to like read across the page.
Yeah, okay, so
that would be something like, what is this?
Yeah, okay, you're right. There's like a monotonicity with the wires.
Yes, there is like some sort of very nice geometric way to say like what a string diagram is and what deformations are allowable.
Okay.
But I'll just say for now that
you've got to preserve reading order kind of thing.
Yes.
Okay.
Well, no.
You don't have to, but if you're not doing it, then it's because you're doing something.
Yeah, like for example, like the interchange law.
That one you're allowed to swap.
It's not going to preserve the reading.
Because you're not really, yes, but you're not bending, you're sliding along wires.
Yeah, I mean, we could do a bend like this, but that would be interpreted as something like we've got some adjunction and we're inserting the zigzag into our thing.
Okay, cool. Thank you.
Okay.
Okay, this is nice. You figure out that it has to be F2 and G2 because that's all you've got for the, okay.
And we could do something similar for, for our eta, our unit.
Wait, sorry. Oh, wait, so sorry. So what were we doing? This equality here is the thing that says eta is monoidal.
Yeah, epsilon, yeah.
Epsilon, sorry. I see, okay.
Yes, and if you want, so there's another rule, right?
Eta would look kind of the same, but like flipped, right? Like you'd have a cup in the top left and the zigzag and like...
Exactly, it should look something like this. And we can drag this through and we'll get
you'll pick up a G2 and then F2. Yeah.
Okay, right. And so again, we're ignoring the unit condition, right? Which... but we're okay with
I
that.
believe it works.
Um,
Is there like a, I don't want to, I feel this is a derailing question, so I don't want you to answer it really, but like, is there a way to do this in an unbiased?
yes.
Okay, cool. Is that why I'm allowed to just pretend that the zero condition works? Because
Pretty
you can
much.
just do this unbiased.
Yeah.
Okay, cool.
Okay, so let me get a bit of. Let's see.
No,
I can make
okay.
it smaller than the corner. Okay, so the thing we're asking is, can we say anything interesting? We know already
It's some academic validation.
that F has an Oplax monodal structure.
Yes, because it's a left adjoint. Okay.
But we're also assuming in this case that F has a lax monodal structure. Right, that's part of the definition. We've got
Oh,
this
sorry, yeah,
F3.
because we're saying it's a monoid. Yeah, okay.
So,
Oh, if you're lax and
much?
oplax, do you get for free like a two-cell filling the back and forward?
Oh, right.
Is there any compatibility between lax and
yeah, so
oplax?
we've got something like this. Um, uh,
Yeah, like you have one map is laxness and the other map is oplaxness. Is there a
well,
or not a two-cell? That doesn't make sense. Is there something in there?
are these inverses? Like,
Are they inverses would be one thing. Yeah.
shall we find out?
I'd love to find out.
Okay. So, we've got this F2,
Yeah.
and let's recall how we defined the induced Oplax structure. So we used the G2 structure, which went from, was it box? I get confused now. It must be box.
Yes.
Which had this box, and we had a G2,
Yeah.
and then we did an eta, so eta squared.
Yeah.
To get our F2, and then we did our
You get a
epsilon
to get rid of that G, and then you've got a box. I just don't like where, wait, that guy is labeling here, right?
Oh yeah, sorry. Box and circle.
Yeah.
Okay. Yeah, right? Okay, good. And this was F. So this goes from F box to tensor F.
Yeah.
And now we want to ask, let's just stick our F2 down here and see if we get the identity.
Oh, because this is what it would mean for them to be inverses. Yes, of course. Okay. Oh, so we get to like do rules and stuff.
Yeah, okay. So we know some rules. Is there anything?
I see a massive rule, which is that if I just, here's what I see is I see something that looks like this. Or, well, I'm not too sure which way. I see locally, I can't figure out the rest of the wire, but I see a wire with an F2 and a G2 on it going through here.
Yeah.
And I see some things crossing it.
Yeah.
So I know that, and if I scroll up, I could see that the one which has F and then G is the guy that comes from the unit. So this epsilon in the top left, I could drag it down. So I'm allowed to write this as F2. No, wait, sorry, the whole point is I'm getting rid of them. Sorry, okay, wait. So I take this epsilon, I drag it through. So I'm going to get just my tensor one that goes from,
sorry.
Oh yeah, sorry, we're on different, oh yeah, sorry, I'm writing down here. I will have an epsilon that's just down here now. And then let me see if I've like missed anything. So I've pulled it through.
Epsilon.
Wait, yeah, nope, sorry. I see exactly what I'm going to get. Okay, I've pulled through my epsilon, but I've only pulled through the wire from like here, this loop here. So I still have down here.
And it's not just an epsilon now.
It's an epsilon squared and an eta squared, like this. But that's that.
Yeah.
Because this is yank. This is one of the things. Okay. And this is tensor tensor. And this is
F squared.
F squared.
Yeah.
Oh, okay, yeah, cool. Huh. Okay, so the induced Oplax structure you get from being a left adjoint is like for free compatible in the sense that it's inverse to the lax structure that you've got from defining it to be a monoidal adjunction.
Yeah.
Wow, that's really nice. That's good to hear.
So, I mean, there's the other direction to check, but that will correspond to pulling like an eta.
So this is the fact that I almost said
Mm-hmm.
at the beginning, which is when you have a monoidal adjunction
Mm-hmm.
and the right adjoint is lax.
Mm-hmm.
Wait, when you have an adjunction
Mm-hmm.
between monoidal categories
Yeah.
and the unit and co-unit are monoidal.
Wait, what kind of adjunction? A junction of lax monoidal functors or of lax?
Wait, yeah, good question. Lax. When you have two monoidal categories
Mm-hmm.
and an adjunction between them of lax monoidal, a monoidal adjunction of lax monoidal functors.
Yeah.
That's what we started off with.
Yeah.
Then not only does the left adjoint also have an oplax structure, that oplax structure actually makes it be pseudomonoidal. It's an inverse. Is that the right word? Pseudomonoidal?
Strong.
Strong.
For some reason, but in other contexts, we'd say that's we'd say pseudo.
Okay.
But yes. Okay. So let's write that down.
Could add another page instead of.
How do I do that?
Oh,
plus.
Yeah, there you go.
Okay.
Now you're on a new page. But now we'll use this.
We've got one long
page.
page.
Perfect.
Okay. So what have you noticed?
I've noticed that. Are you going to write it? No, you should write. You should write. You're teaching.
Okay. So the first thing we noticed is that if G has a lax monoidal structure, then any left adjoint. Okay, yeah, I guess.
So I'm going to say like this is just like in cat, right? Like
oh yeah,
it's an adjunction, just like
in cat between monoidal categories.
And there's no symmetry anywhere, right? Like these are just monoidal categories. Or are we assuming they're symmetric? Does that matter anywhere?
We can.
I've never considered a non-symmetric.
So we'll talk about like how this generalizes.
Okay.
And it'll include, symmetric.
Okay, cool.
But we've not mentioned symmetry yet.
Okay, cool.
Then any left adjoint?
Any left adjoint to G?
To G? Well,
up to, okay. No, fine, okay.
I mean, technically we could, I mean, they're all going to be isomorphic and they're going to,
anyway.
Okay. Then, okay, fine. A left adjoint.
No, and write any, it's better.
As the point was that we're going to say not necessarily monoidal, right? It's just
sure, yeah.
An arbitrary left adjoint functor to G.
Well, I guess I've given you the context above, so you could just write then F
I know,
has.
but I didn't. Naturally inherits.
Yeah.
An oplax monoidal structure.
Yeah.
Okay, that's number one.
Yes. And then number two is that if the unit and co-unit are monoidal adjunctions, then G. Oh no, wait, sorry. If G also has a lax monoidal structure.
Yeah.
So which is the same. Oh yeah, sorry. Okay. Yes. So it's when you say the adjunction is monoidal, this part that tripping up, like that actually implies two things, right? Yeah. This implies that first of all, F is also lax monoidal.
Yeah.
And that like eta and epsilon are monoidal.
Yeah. So it's an adjunction in like mon-cat lax.
Yes, sure. And like there's some other stuff about units or something probably. Like you should say the unit guy. There was some other stuff, but those
are the two cells in mon-cat lax.
Okay. Yeah. Okay.
So
basically, the adjunction lives in like, I mean, is it always going to be the case that we have some adjunction that lives under a forgetful functor and we like lift that, we say like if that adjunction comes. Okay, good to know. Okay. If the adjunction is monoidal, then F. Oh, sorry. Then the oplax structure from part one makes F be strong monoidal, or like is inverse to the lax monoidal. Like,
yeah. So then F is strong monoidal.
Yeah. Stoon.
Strong monoidal. Right, and moreover, its laxator is inverse to like the mate of the laxator. So then F is strong monoidal. i.e. the colaxeter.
Which is from 1. Wait, do you call it the colaxeter for an oplax functor, not the oplaxeter?
That just sounds wrong, but I mean, people take colax monodal functor.
Oh, okay.
There's maybe
Okay.
HPV as well. Then the oplaxeter is invertible.
You have to put it in scare quotes because you don't like that much.
I've not really said it before, I did.
Okay.
Right, so we
Okay.
see that we've got this extra strong structure. Right, so there's an example
Yeah.
of doctrinal adjunction.
I just want to check like how like if the dual statement I'm imagining is the
Oh.
obvious dual statement, which is just I want to say that like you look at F and you say that if F is oplax, then G inherits a lax structure.
Oh, that is also true.
Okay,
Yes.
you like the same. I'm not actually like switching which one's lax and oplax. It's just you say them in the other order. Like you
Yes.
say if F is oplax, then G becomes lax, and if G is also lax, then that oplaxator from the first part becomes the bit that makes G strong.
Yes, yeah.
Okay,
So
cool.
a right adjoint to an oplax functor
Is strong.
It becomes a lax monodal functor.
Yeah.
But an oplax right adjoint to an oplax functor is strong.
Okay.
Okay.
But there's a dual statement which isn't true, which is that if G, the right adjoint, is so you have an adjunction F and G. If G is oplax, that doesn't tell you that F automatically becomes lax, I'm guessing.
No, right. So there is an ordering.
Yeah,
the
okay,
left
that makes
corresponds to the oplaxness.
Yes. Okay.
Cool. Right. You can try and like the point is that the caps and cups go in a particular direction. Okay. So I don't know how long we've been talking, but
Oh, like so 45 minutes.
Oh, okay, cool. So maybe I'll give some other. I can just list. So my plan was like maybe list some other examples of where we see this, not work through them in as much detail, but and then I'll like give you this statement.
Okay.
And the thought was maybe we can actually like prove the statement using similar arguments where we've just done with string diagrams.
Okay.
Maybe we don't need to actually do the proof because it would look in some way similar to what we've done. But yeah, it could take some time.
Okay, we'll see.
So this is an instance of doctrinal adjunction, and the idea is, a monodal category. Oh, this is sort of the connection, I guess. A monodal category is an algebra
for a monad.
For a
two-monad.
Two-monad, aka doctrine.
Which two-monad?
We talked about it before.
Oh no!
Do you remember when we talked about clubs?
Oh, yeah.
It's essentially,
okay.
if you've got a category C, you can build another category whose objects are trees.
Yes. I remember this. Okay. It's a bizarre world we live in where if you'd have said double instead of two, I would have been like, yeah, sure, I know that.
Oh, okay.
I think you told me the story in the double case. For double list monads, we found that we recovered.
It was kind of complicated, but that was really for two monads. The point is a double list monad.
Oh, does something pretty. Yeah, and it does. Okay.
A lax double.
Yeah, I do remember this now.
A lax double monad.
Okay. Sorry, yes.
On span set.
Okay, so you have actually told me this exact fact before, and I just forgot.
Well, yeah. I mean, technically we're talking about symmetric monodal, but we're going to see that. That's just it.
Okay.
So a monodal category is an algebra for a two monad.
On cat.
On cat, yeah.
Sorry, I just want to. Okay, yeah.
On cat. Right. So it's actually maybe it is worth sort of saying what TC is, but TC morally is it's given by trees.
Yeah.
Like formal expressions
of n-ary trees, and you just.
Well, it depends on what sort of way you want to express them on it. We could talk about n-ary trees.
Oh, would this be like an unbiased
thing?
Okay.
Or we could talk about
two-ary. Binary.
Well, binary or
nullary.
Or nullary, because we can have like ones.
Yeah.
and like elements of our
Mm-hmm.
of the category C.
Mm-hmm.
And morphisms are given by generated by morphisms which like correspond to associators, so stored in sort of rotations of the
Mm-hmm.
tree, and like canceling out these things.
Sure.
And those are, you know, isomorphisms satisfying certain
Yeah.
associativity, Pentagon laws and so on.
Sure.
As well as morphisms just on the roots. So we, you know,
Yeah.
if we've got morphism C to C prime, we could do a morphism from that tree to this.
Mm-hmm. Mm-hmm.
Okay. And you can sort of see that if I've how having a monodal structure on C gives me a map from this category. Right? I just realized
Yeah,
this
you actually like
as
write
like
it down.
one
Yes.
tensor.
Yeah.
Okay. Now,
And somehow like associativity plays into the fact that you. Sorry, I'm trying to think about like what it like. Yeah.
the tree rotation law.
Yeah. Okay. Yeah.
Well, it would just say that I need to, so for example, we have a morphism from,
Yeah, it somehow doesn't matter. Sorry, like to me, associativity says that this tree would be interpreted the same way as this one, which like looks bad, but sorry.
ah,
Just in the sense of like if I do like, because here I would like read bottom to top right and I go like, oh, first I take C and D and I tensor them, then I trace up and I do that tensor with one. This kind of says like, well, my bottommost guy is one, so I tensor it with something. Well,
no, so
okay.
the
No, I see.
associativity says that this tree, it inserts a primitive
Oh,
morphism from,
sorry. Yeah, obviously. It's the associative operad. Yeah,
yeah, yeah.
okay. No, sure.
So we could
That's
ask,
way better than what I wrote.
like,
Okay.
so there are
Yeah,
various
sorry.
monads, like there's one which identifies these,
Yeah.
like quotients out these trees by this relation, but there's others which just declare this
Just
to
throw
be
in a cell.
check in an isomorphism.
A nice.
And that
Okay.
must be realized as an isomorphism in C from A tensor B tensor C to
Yeah.
A tensor B tensor C.
Gotcha.
Right. And then we put in the pentagon axioms
Yeah.
into our
Okay. This is kind of interesting. Yeah, this kind of category theory is super foreign to me, but it's like, is this like some sort of like formal category theory in the sense of like what you're building up is like just syntax for monoidal structures, and then you're going like, oh, I realize it by like actually instantiating like this formal symbol corresponds with this. And here it's like, because it's TC, actually the nodes are objects of C. You don't really have a choice on the objects, but you're like picking out something for the other parts of your tree. You're like, do you see what I mean? It's like you're specifying a formal shape and then you're sort of like realizing that in some semantics, you know?
Yeah, so we talked a bit about this, like not necessarily all two monads are of this form, but we talked about like two monads generated from clubs,
We did talk about two monads generated
right?
from
Where
clubs.
you like pick
The
some
audience
sort of
doesn't know we talked about two monads generated from clubs, but
sure. So I'm not sure. I don't have.
I'm sure
But
they're still watching and like.
let's recall that in a club, the point is a
Yeah.
club is sort of like. So this looks a bit like, you know, terms given some like Lever theory with some symbols, and then you got some equations.
Yeah.
Instead, we might have like some terms of some n-ary terms, and then some and they like each term has an arity. But we might have, rather than say two terms with the same arity are equal, like add an equation,
Yeah.
we add a morphism between them and say which permutation of the arities it. Do we?
Okay, yeah.
Right. So
Yeah.
we sort of talked about that, and that's like, so if we talked about symmetry, then um, that's where that would come up.
Yeah.
Right? Because you've got this map. We've got tensor, which is arity 2. We've got tensor, which is arity 2. And then we add a morphism between tensor and tensor,
Which corresponds to the permutation swap.
yeah,
Yes.
all this like tau, whatever.
Yeah.
So there is a way of building up these like categorical algebra structures, which looks a bit like defining an algebraic theory.
Okay.
But there are other two monads. So for example, like free completion under a certain class of limits or colimits.
That's a two monad.
That's a two monad.
Because if you do it twice, you could have done it once.
Well,
okay, yeah, no, but actually, yeah, wait. So what is the like? What's the map from like just what do you do
What's the do it twice?
Yeah, what's the do it twice to do it once map? Because now I've got a bunch more limits. I can't just like figure, like what do I do with them?
Oh, um, the do it twice to do it once. What's a nice way of um hmm.
I mean, something I can imagine. Here's a guess.
Mhm.
Wow, really a lot of bravery here. I'm just
Yeah.
gonna make a guess that like how if I've done this.
Oh, we're talking about the actual like pre-sheaf
Oh
thing.
yeah, sorry. Like this one, I'm like, here's my obvious guess. Like, how from this do I get a guy just into C-op to set? Well, I just use the diagonal. Like I just this guy means I need to give you two C's.
Mm.
So I just like
That's not the double. The double is COP set
oh,
op
whoops. Yeah, okay.
set. Okay.
Oh, okay. Yeah, no, you're right. Well, if only it was this thing on the right, I would know what to do. Okay.
So we can that's a good
Like
question.
how from here do you get a C-op to
Oh,
set?
sorry, I'm
Oh, you were about to. Okay, we'll let go
it's
of the
erased on
button.
my screen.
Okay, that's fine.
How from there do you get a C op to set? Um, I mean, that's how from there do you get a C op to set? I guess you right. Okay, you've got C, well, I can you got C op set,
Uh-huh.
which goes via the Oneida embedding
Yeah.
into C op
Set.
set
Op to set.
op set.
Mm-hmm.
And so we talked about this as well, it turns out recently.
Okay.
Right, and so you know that any map into a co-complete category,
Factors through.
yeah,
Yeah. Okay. Yes.
you get this co-continuous map. So
Yeah.
we can just take the left count extension
Gotcha.
of the
Yeah.
along the unitary embedding of
Yeah.
the identity. Um,
I see. Okay. But there's not a. Okay. You
and
don't
maybe
off the
this
top
is
of your
like
head like a slick way of saying what that does.
I mean slick.
I guess by
I know
slick, I
I
just
would
mean
want to
like
start writing
by
it
slick.
Kelvin
Yeah,
form.
I mean like by slick, I always just mean like take C to be this category, and then like what I know what one of these guys looks like. I know what one of these guys looks like. How do I turn one of these
Mm,
guys into one of these guys?
I mean,
But
like considering just C is the point, we've got a map from set op.
oh, you're
Set.
right. So if you take C to be the point, you just get a map from set up to set to set.
Hmm.
What's that map? Just like evaluate on terminal or something, or evaluate like on the point or something.
Yeah. I mean, should it just be the um I don't know.
Me neither.
Okay. I mean like
That's okay. We don't have to answer this now. I'm sure you'll tell me
but
another time, and then you'll be like, as I once told you.
yeah. I mean yeah, it's natural to see that there's an adjunction
Mhm.
defining this thing and we could
Yeah.
so and it probably is quite elementary and
Okay, so that's fine. No,
otherwise
okay,
thing.
cool. Sorry, go back to what you were actually talking about.
Okay. So you've got this map DZ down to C.
Hmm.
Now, so we've got a monodal category is an algebra for a two-monadal cat.
Yeah.
What do we think a lax monodal functor is?
A lax monad morphism.
A lax monad morphism.
Nice.
What do you think that is?
Which is interesting because, oh, okay.
I'm just going to write
One
tensor.
day, you're not going to tell me this now because this
Uh-huh.
would be a distraction, but I know that a category is a monoid in span. I've
Mm-hmm.
never heard a plain category
It's
as
a
an
monad in
algebra for a
span.
monad. Oh, it's a monad in
Um,
span. Like, is it true that just plain categories are also algebras for some one monad on set or something?
yeah.
Ah, okay. I don't know that story, so I'd love to hear that
Not
from.
on set,
Oh,
on graph.
on graph. Oh, okay. Oh, is it the
It's the
free
free
graph? Okay, it's
category.
the free category.
Mm.
Ah, okay. Okay, so this is like a categorification of a. Yeah, okay.
Yeah. So we'll talk a bit about connections in like the one-dimensional case.
Okay.
Um, Now, obviously, like it's kind of interesting that cat is a two category,
Hmm.
whereas categories of algebras for a monad and a one category are typically one dimensional.
Hmm.
But Okay, so this is what you might expect the definition of a um, of a sorry of an algebra morphism
Never. I would
to
never
be.
expect such a thing. Here's what I would expect it to be.
Uh,
Sorry,
okay,
that's a terrible arrow. My screen's much smaller
and
than
you're
yours.
going to call that lax or upright?
Ah, God. I think that would be called lax because it's the direction I wouldn't. Oh no, wait, sorry, that would be oplax because it goes from the tensoring in C to the. So my guess is the lax one is this one.
Yeah, so well, that is certainly consistent with what we declared, right?
Yes.
So imagine this is just like c squared, and
Yeah.
the tensor is telling you how to do
Exactly.
that. What we saw was a map from f squared,
Yeah.
then tensor,
Exactly.
into f after tensor.
Yes.
Okay, so this is indeed a lax morphism of algebras, and an oplax morphism goes in the other direction,
Cool.
and a pseudomorphism
Invertible.
is invertible, and a strict morphism
Id.
identity.
Nice.
Okay,
Okay.
precisely. So.
Oh, okay. And what's interesting is when you have, so this is
Oops.
something, I don't know, I just know.
Sorry.
Oh,
It did.
wait, did
Oh.
you erase it? Oh no, it's the next. Oh, okay. No, wait, who?
Okay.
Okay, good. Um, the no, just in this square. So when we had like a lax and an oplax structure, and we were like, oh, are they invertible? What's interesting is you'd get a square with like a sheet filling it, and normally you'd glue those two squares along the boundaries, and this is like makes an air pocket. You could have some non-trivial 3-cell in the middle, but we're saying there isn't. It's an id. Like,
Sorry, what was this for?
sorry, remember when we had this whole like if the right adjoint is lax and the left joint becomes oplax. If it's also oplax, then there's some like fact.
Oh, okay. You were talking about, yeah.
I'm saying that like normally if you have a lax and an oplax structure, all you'd be able to do is you'd have these sort of like two cells that fill the square, but there could be a 3-cell connecting them. And what was interesting is there isn't. It's the identity. They actually like that the inflated balloon like flattens, right?
Yes.
Okay.
Right. This is a diagram in your 2 category in which the monad lives.
Yes.
So it's not got 3 cells. But yes, so we had more
Yeah,
dimensions,
okay,
we could do more
yeah.
things. So this is not a 3 category, but it is a 2 category. So, well, actually, sorry. I've given you 3 different candidates for the different ones. So 4, right? Lax, oplax, pseudo, and strict. Okay. But in any case, we can come up with a reasonable notion of 2-cell.
Yeah.
And it's just a 2-cell, like on the underlying morphism alpha, such that the obvious pastings work. So imagine we've got like a psi on the back. Then we ask that if we do, so we can start from tensor D after TG, and we've got 2 options. We could do T alpha, and then we could do psi. Hopefully this sort of looks familiar.
Yeah, but you do that, I'll draw a topology. It's amazing. So like for me, what you're saying is like that this, sorry, this is meant to be the bottom one. Oh, this is going to be terrible. But it's going to look something like this.
Oh, wait, let's that up.
This is my picture of what you're drawing, but it's not very good.
Oh, I see.
You see what I mean? It's like if I do the back face, the back, this T alpha, like, yes.
Yeah.
I do that guy, then the bottom sheet. That's the same as doing the top sheet, then the front ellipse you've put in. Yeah. Okay. That's the picture I see.
But doesn't this look like the
Do you know what that looks exactly like, Jason? Actually, I was just telling you about these. This looks like okay, this looks the same as saying that you have this is the same as what we saw for when you had a monoidal transformation.
Yeah, exactly. Right. A monoidal 2-cell is an instance of a 2-cell for a category of algebras.
Okay.
For a 2-monad.
Okay. So it sounds like generally algebras for 2 monads and cat are interesting things to study.
Yes.
Okay. And they
there's
remind us of monoidal functors and
all sorts of interesting things to say about these. But for now, maybe I should just get to the the actual statement of doctrinal adjunction.
Yeah.
But what we're observing is that if we've got a lax morphism of T algebras, then a left adjoint on the underlying
Yeah.
morphism and the
Mhm.
carrier, automatically inherits a structure of an oplex morphism.
Yeah.
And if we've got a lax adjunction, I mean, I'm saying everything I said, but instead of
Yeah.
monoidal, I'm saying T algebra.
Yeah.
If we have a lax adjunction,
Mhm.
then the left adjoint is automatically strong.
Yes. Is
Okay.
there a way I can see that by drawing a picture, pardon me, like I have in green with the like, as in like when you say I have a left adjoint here, what I'm imagining is I now have on my front, I have like, well, I have, is it like, so for example, wait, let me see if I can say this. Basically, when you give me an adjunction downstairs, you're turning my like, sorry, originally I just have something and you're giving me an adjunction downstairs, which is giving me like letting me realize a bottom flat sheet and the front semicircle. And somehow my adjunction also gives me a back semicircle, and therefore I can infer that there is a top sheet that glues along it or something.
Right.
Do you see the picture I'm trying to?
There is a picture we can draw here, and it's one you've probably seen Jose draw. Whoops, GC. A few times before. So let's I'm just going to call this H and K, because
Sure.
you know T is anything we like now.
H and K, H, I. Oh, okay, yeah. No, go for it.
So let's say we've got G, and we're assuming we have a left adjoint to G.
Yeah.
No, that's not what I expected. I'm used to a different
Yeah.
editing software. Okay, so we've got some.
Do we really want to call G the guy who goes from C to D? I worry you might get confused. By which I mean I'm
I'm
gonna
not
get
going to get.
confused. Okay.
Fine. Okay, let's. Right, we've got this map here.
Which is, yeah, what I was trying to draw as my like front almond shaped thing. Yeah. And you've got a back almond shaped guy. Yes.
Oh, I see.
You see, yeah, you see what I'm like, yeah.
Okay. And if we sort of, yeah,
Skew it.
squint at this a bit, we now see like, maybe I can actually do this in a, do that first. Can we, so F is now sort of, yeah, this kind of works. What was this?
It's an F apparently.
That's okay. So let's like, let's just ignore the G's.
Yeah.
And this is now a K from TD to, this is now H. Now, doesn't this look like a
Yes, it looks exactly like what we
an
want.
oplex thing, but now we're going backwards. But
Okay.
it's
Yeah. That does look exactly like that. Yes, I agree.
Okay.
That's okay. That's kind of what I meant. So like the image I'm imagining is, say in this picture you've got, see where you've drawn identity lines. Imagine instead shrinking that to a point, so you just have like an almond shaped guy.
Okay.
And then what I'm saying is to like, what's the move you're doing here is the kind of trick, is you're saying that, oh, I want to give you, I have a sheet of paper with an almond glued on each end, and it's the bottom sheet of what would be a cylindry type thing. I want you to give me the top sheet. Well, a top sheet should be a path from like the top almond at the back to the top almond at the front, but I just do it by going through the bottom sheet and then back up at the end. Because this F that goes from D to C when is the top end of the almond. I don't think this is going to be helpful for anyone to be hearing this, but I can see a nice picture that I will make for you.
As long as you've got a picture that you're happy with.
Okay. I think, sorry, just on a time thing, I think you should give me a punchline theorem and end on a cliffhanger.
Okay, I can end on a cliffhanger. So we've got this two category.
Oh, just we have a two category.
Well, for any two monad.
Oh, sorry, for any two monad, we have a two category of algebras for that two monad.
Yeah.
Yes.
Okay. In fact, we've got lots of two categories.
How many two categories?
Well, we've got at least four. Strict, pseudo,
sorry,
lax,
yes,
and
of course.
oplex.
Okay, yeah.
But there's sort of, let's just think about lax and oplex. I mean, we also know that every strict thing is a pseudo thing, and every pseudo thing is lax and oplex.
Yes.
But there's oplex and lax. There's a there's a symmetry to them. Neither is an instance of the other. So it's like there are two different notions of morphisms that we want to
Wait a minute. That sounds so double.
keep around at the same time. Okay, so a natural thing, yeah, thank you. A natural thing we could do is we could build a
Double category.
double category.
Yeah.
Whose objects
are algebras for the two monad, whose weft, as I hear some people say, whose weak, loose. What do you guys actually say?
Well, here there's not really going to be this
Oh, it
pseudo.
doesn't actually. No, it doesn't make a difference because they're both. Yeah, this is an interesting type of double category, which is where they are somehow like equally strict, both your vertical and your horizontal.
Yeah, I mean, it's like it is the natural. It's like a strict internal category in cat. The double category whose objects.
What letter do you like to use for algebras?
A, uppercase A for the carrier, lowercase a for the structure map.
Okay.
Objects are D algebras. Now, there's various versions of, there's strict, pseudo, lax, off-lax T algebras.
Yeah.
Let's just talk about strict for now.
Oh, okay. So you have the choice of all these strictness things for the objects and for the morphisms.
Yes.
But everything's
okay. There are reasons where we're going to be quite happy just talking about strict.
Okay.
Objects are T algebras.
I'm drawing what
Oh, you're drawing a
I'm just going to draw
okay.
I was going to draw the horizontals and the looses. Okay. Sorry, no. Yeah, let me start. Oh, let me start with okay.
Tights. Wait, no. I want to say verticals.
Yes, that makes more sense.
I'm going to go
verticals. AKA
actual off-lax T algebra morphisms. I'm just going to say off-lax morphisms.
Horizontals, aka the weft.
I'm just gonna.
Whoa! Oh, okay. You've moved so many of my letters around. I'm not even gonna.
Horizontals are. Oops. Okay, whatever. Are off-lax morphisms.
Oh, I guess I actually don't need to draw little symbols on my arrows then, because we're actually writing the vertical ones as verticals. As in, sorry, I was going to O for off-lax and L for lax or something like this. So that's okay. So what is a wait? So this is lax and then off-lax. What is the composite of a lax and an off-lax morphism?
Well, you don't. The point is you can't.
Oh yeah, no, sorry, you can't compose them. Okay, so what should a two-cell be?
I mean, the point is you can compose the underlying.
You can compose the underlying morphism.
So here's a picture we can draw. Let me be careful with how I draw this. So I mentioned we just got the boundary.
Yeah.
And now we're going to assume that we've got some these ones that these ones are lax, right? That's how we defined it. So these go down.
No, wait. When you say these ones, sorry, what's the line? Is that the TA to TC?
Yeah.
Okay. Sorry. Yeah. Okay.
Right. That's.
Yeah. Okay. Sorry. I thought you're
obviously
you're pointing at that one.
Oh, okay. Sure.
Okay. Yeah.
And these ones are up-lax.
Yep. So they go up.
Okay. We're going to ask for a cell.
Ooh. Okay.
That goes in this direction.
Wait, and that's in the bottom square. I'm trying to like see which way, like where does that red cell go from to? That's the A, C, B, D.
Let's call this phi 1, phi 2.
Sorry, so you're drawing a box with like,
call this
green here. And then you've got I don't know if I have a blue pen.
Yeah, that's right.
Sorry, yeah. And then, sorry, yeah, and this is blue. The back and the front faces. And then you're now asking for the reds to be, I definitely don't have a red pen, but that's okay. And then the reds are the guys we're going to put on the top and the bottom.
Yes.
Okay.
Okay.
And those should both look lax.
Those
By
should...
look lax, I mean they go top right to bottom left.
Wait, which ones?
The red ones.
Oh, yeah, yeah. Yes.
Okay.
But there's obviously a condition we could
Sure.
impose here.
Obviously, there's a but.
So, like, we could start. Ooh.
Oh, yes.
I'm not
Yeah.
going to bother drawing the labeling the one cells,
No, but yeah.
but let's like we could do. So let's say we
can draw the
start.
path. Wait, can I
You've got a
put,
highlighter.
like? Oh yeah, I do have a highlighter.
Okay, I'll tell you which way to go. TA to TC.
Yeah.
Then down to C.
Yeah. And then
down to D.
Yeah, that's path number 1.
Okay, cool. So let's say we start TA to TC. Sorry, that's not path. Well, that's, yeah, sorry, yes, that's, and then we go to C, and then we go to D. And so we've got this path of length 3. Now, one thing we could do is we could take the first two and do our psi 1, and then we could do an alpha to this thing. And then we could do a...
So going from this path to this path to this path.
Yes, and then there's one more. We could do a phi 1 to the first two.
Okay. I like to, yeah. This is, okay, yeah. This is really like a lot of these, looking at these like ways of, this combinatorics of like, how do you take a path sort of from like the spine of a cube through, comes up a lot in like, in DG nerve constructions. It's kind of a cool guy. I'd be interested to know if the combinatorics are actually the same. But like, yeah.
I mean, yeah, like if these were all, I guess, lax, we would have it as slightly
No,
different
it's kind of
starting point.
interesting that a separate thing, but like it's kind of like when you label like a 3 simplex in the DG nerve, your arrows don't all just go like toward. There's some interesting arrow direction, and I wonder if it is the same.
Yeah, like
anyway.
there is sort of like 2 canonical, like you can order all the paths. By,
Yeah,
like,
you
the way
label them
get
like
from
you give
to
them
the other.
X, Y, Z coordinates, and you do the like keep as many zeros at the beginning as you can for as long as you can order.
Oh, okay.
Yeah.
There we
Okay, that's so beautiful.
Okay, so that's what a cell looks like.
Yeah. Okay.
And so what's the punchline?
I don't know.
Okay, I need a thicker pen for.
Oh, it's that.
So claim. I guess, well, there's really one fundamental thing that has to be proven, and then there's a bunch of stuff we can derive from that based on the properties of double categories. And that is, so let's imagine that, assume, I didn't say what T was a monad on. T is a 2 monad on K. Then there is a map T alg down to,
which is like, I'm going to write, I know you won't like this, sorry, but I'm just going to keep it in my head. So this is like T alg. Oh, no, definitely not that one. Wait, sorry.
You're going to draw a...
No, I was going to just write like T alg strong and then like lax op lax. Well, as in the objects are strong, strict, sorry.
There is a convention. Usually we'd write, like, if we wanted pseudo, we'd write.
Oh, okay.
So I'm just
I'm sure there is a convention.
But you can leave that.
Thank you.
Lax of lax, sure.
Yeah.
Okay, there's a map down into quintet K.
And sorry, quintet, remind me, is the one where it's just squares. Okay. The 2 cells are commuting.
The point is, no, the 2 cells are cells. So that's sometimes...
Oh, okay. Sorry, yeah, okay.
Right. So note in particular that any 2 cell in T-alg gives you a
2 cell in square. Yes.
Yeah.
Oh, and that's precisely what this map is. Sorry.
Yeah, yeah.
Okay.
It just takes the bottom of the cube.
Yeah. Yeah, okay. So in particular, it also tells you that like this quintet K comes with a, I mean, I don't know, I'm just going to write in more words here. Like this is very precisely like, as in this imposes an orientation on the two cells.
Right, I
And
guess
it would
there's
be the one that
two
like,
quintet Ks, yeah.
yeah.
And we could have like, why do we take the verticals to be the
Sure,
operator?
yeah, okay. I'm just, with the conventions we had, like, this is what happens. Okay.
Sure, yeah. Okay.
Creates conjoints.
hmm
Only I knew what that meant.
And my claim is that all the results, like,
Oh, like this whole right adjoint implies left adjoint has up lax.
yeah.
Right adjoint, left adjoint lax implies strong, all this
I
stuff.
guess there is another claim, which is um, uh, a morphism, or rather, I could just write, say, companions in T-alg
Yeah,
are,
strong.
well, sorry, pseudo.
Okay.
So I can still recover,
hmm
you know, how do I detect whether a lax or an oplax morphism is pseudo? It's precisely one which has a companion. Now, I don't know how familiar you are with conjoints and companions.
I feel like they're the things that you naively, it's like do a transpose.
Right.
As in, like, take something of this shape and give me something. Like,
Yeah.
realize some thing with a vertical in it as a horizontal. Yeah,
Yeah.
something. That's how
Yeah.
familiar I am,
So
basically.
companions and conjoints take verticals to our horizontals,
Yeah.
or vice versa, I guess,
Mhm.
or they express a relationship between the two.
Sure.
Companions say morally that like these two are the same,
Okay.
and conjoints say that these two are like adjoint in a certain sense.
Okay.
The point is that if you've got a vertical from A to B,
Yeah.
its conjoint will go from B to A.
A. Sure.
So in particular, a conjoint in quintet K
Mhm.
is the same thing as an adjunction.
Gotcha.
Right. Quintet K has all companions.
Yeah.
If I want the companion of a vertical, it's just that same morphism expressed as a horizontal.
Yes.
Okay.
Yes. Okay. Yeah. And then, sorry, this is the part we have also talked about this before. The terminology to create something means what?
It means
Because I
that
always get this wrong. I've taught the category theory course at the university so many times, and I always have to look it up.
Yeah.
Like creates means preserves and no, preserves and reflects.
it means preserves, reflects, and lifts.
That's the third one that's always missing that no one ever defines.
Yeah.
Yeah. Okay. Preserves, reflects, and lifts.
So, and the lifting bit is important. So we can just think about what this, so I just told you that conjoints down here are adjoints. So that says if I've got some morphism, some vertical up here,
Yeah.
um, and so that maps down into just the underlying map from A to B.
Yeah.
And let's say I've got a conjoint downstairs, which is the same thing as a right adjoint.
Sure.
I should have started with a loose, it doesn't matter.
Yeah.
We've got a right adjoint to an oblax. Previously, we were talking about left adjoint to laxes. So, you know, there's a picture like this.
Yeah.
So if we've got an adjoint, then we can lift it to a conjoint up here.
Okay. Yes.
Right. And we know that we've seen that if we've got a right adjoint to the underlying underlying functor of an oblax algebra morphism, then we get a lax algebra morphism.
Was it
right
lifted
here
up?
or something.
Okay.
And it has this nice relationship. So we can look at what conjoints are, but they're precisely these sort of pairs of lax and oplax where the like laxators or the things filling the squares are mates in that previous picture.
So this is why, so I was like, oh, is it always going to be the case that, because when we passed from monoidal categories, we said like, oh, it should be a functor on the underlying category. I was like, is there some forgetful functor lying around? But the forgetful functor is essentially just forget the algebra structure on your carrier. That's what it is. Okay, and it happens to be the case that for monoidal categories, when you realize them as algebras for the two monad on cat, forgetting the algebra structure on the carrier just means consider the underlying category. Okay, cool.
Right. And like just one analogy that might sort of make this seem like it should be true is think about morphisms of algebras for a monad-on set.
Right.
Let's say we've got monoids. We can ask, let's say we've got two monoids and we've got a morphism of monoids from one to the other.
Yeah.
Let's say that's invertible as a function.
Oh.
We know that the inverse picks
Yeah.
up the structure of an
Yeah.
algebra map.
Yeah.
Right. That's precisely because the map down from T-alg into set or in general under C,
Okay.
is conservative. It
Yes,
reflects
yes.
it reflects
Interesting.
inverses,
Okay.
which is the same thing as it creates
Creates.
isomorphisms.
Yeah.
Or creates inverses homomorphisms.
Okay, that's a really cool example. Okay.
And so here, like, what's the two-dimensional analog? Well, it is true that these maps create, like, T-alg creates, if you've got a strict map of T-algebras, then it'll create inverses to that. But we've got these weaker notions.
Which is these adjoints, which is these conjunct, and like it still creates them.
Yeah.
That's so
And
cool.
okay, I didn't. So there's a bunch of other examples, like so.
You can't tell them to me.
Okay.
I think we should.
Yeah,
That's
yeah.
another great thing. I would love to hear
But
some
there's
more
lots
examples.
of more examples, and
Okay.
it's like, and I think that's kind of interesting. And this is meant to be like, this is a powerful result for like when you don't need to actually check that a morphism is. You can just say, well, it's adjoint on components or something. Therefore, it leads to a.
Okay. And then last question. What's a doctrinal adjunction?
Well, a doctrinal adjunction is a conjoint in T-alg.
Okay, great. I'm glad I got a definition out of the end of it. Okay, that's perfect.
Okay.
Okay, thanks so much.
Well, stop recording.